So good morning, everyone. Today I'm presenting you the work I conducted with Professor Vasile titled Asteroid Deflection under Uncertainty. And I will start giving you a bit of context and motivations behind such a work. And then I will present you the kinetic impactor model already briefly described this morning, which can be used to deflect asteroids, potentially hazardous asteroids. And coupled with that, I will present you an uncertainty quantification technique, the polynomial chaos expansion that can be used together with the kinetic impactor model to assess probabilistic quantities associated to this model. Finally, I will give you some results and the conclusions of the work. So as a starting point, I'd like to quote Victor Zebeheli that wrote in 1982 that conditions for deterministic systems are neither satisfied by those dynamical systems which are encountered by actual physical situation, nor by problems of interest in celestial mechanics. So this may sound a bit weird compared to all the other presentations given this week, but here we're aiming at changing the framework of celestial mechanics in particular to take into account stochasticity. In fact, if we combine this quote with the results of the work by Poincaré and as said by Dr. Valsecchi even decades before, in which it was shown how determinism is not equivalent to predictability because of sensitivity to initial conditions, we have to be able to deal with uncertainties. Moreover, we have uncertainties arising from unknown parameters associated to dynamical systems, and the differential equations describing the system themselves are not, we cannot trust them 100%. And so with this in mind, we're aiming at modeling uncertainty in orbital mechanics. So we start from the kinetic impactor model. For this, we use an unperturbed two-body problem that's defining the underlying dynamics of the asteroid. So we take into account just the gravitational attraction of the sun. And some parameters here are given: the mass of the asteroid considered for the case study, the mass of the spacecraft used for the deflection action, and here the radius of the Earth. So usually for modeling the kinetic impactor, the following equation is used. So the instantaneous variation of the velocity vector of the asteroid is parallel to the variation of the velocity vector of the spacecraft impacting the asteroid. And then there's the ratio of the masses for the conservation of linear momentum, which is then scaled by the beta factor already introduced today, which is an enhancement factor that takes into account hyperelasticity associated to the impacts, or can also model the fact that the impact is also associated to a variation of the temperature, and there are some chemical reactions going on because of the high speed associated to the impact. So there's this factor that's used. However, there's a lot of debate about what's the proper modeling of this parameter and what's the actual value associated to a certain impact scenario. For example, this can be seen because in some literature, the mass ratio is given as the one given here, while in others, below there's the total mass, let's say, the mass of the asteroid plus the mass of the spacecraft. Nevertheless, because we don't have such an accurate knowledge of the value of beta, it doesn't make sense to ask ourselves what's the best formula for the mass ratio, because there's much more uncertainty going on inside the beta value itself than in the shape of the equation. So finally, for the variation of the linear momentum of the spacecraft, we use 25 kilometers per second. Here is the geometry of the case study considered. We gave the value of the astronomical unit, and we assume that the impact is going on at the vernal equinox, at the intersection of the orbit with the vernal equinox, and along the ascending branch of the asteroid's orbit. We took from the catalog a reasonable value of semi-major axis and eccentricity, and then a random choice of the inclination of the orbit given to 40 degrees. And because of the assumption given before, the red ascension of the ascending node is fixed to 0. From here, we can compute the true anomaly associated to the impact. That is the true anomaly for which we have a distance from the sun of 1 astronomical unit. And from there, we can rotate the orbit on its orbital plane such that we have an impact. And we do this changing the value of the argument of perihelium. So here we give some relations to actually obtain the state in Cartesian coordinates from the orbital elements of the asteroids. So the first 6 values are just some quantities arising from the 3 rotations performed from the inertial space to the orbital plane. We have a rotation around the vernal equinox, changing the inclination. Then we rotate around the z-axis, changing the red ascension of the ascending node. And finally, we rotate around the axis perpendicular to the orbital plane, changing the argument of perihelium. Putting this together, we get the position actually of the asteroid in Cartesian coordinates that can be computed using the conic equation given below in equation 7. Some more math is involved in computing the relative velocity between the asteroid and the Earth. We will use this to compute the geometry of the impact. And to do this, we assume, again, a simplified model in which the Earth is on a circular orbit with constant angular velocity, computed here. And then we make use of the impact condition to compute the velocity vector of the Earth at the impact condition. We can do the same, computing the asteroid velocity at the MOID through anomaly, and we compute the velocity of the asteroid. So we need one more equation to before actually computing going into the B plane, let's say, and this is the time of flight between the deflection at the MOID. Here I gave the formula for the delta t associated to 2 different eccentric anomalies whose relation with the true anomaly is given in equation 11. And it's important to notice that this equation describes the time of flight between 2 points associated to the same orbital revolution. That is, it's the difference between time from perihelium between 2 eccentric anomalies. So if we're interested in computing studying a deflection in which the time of flight is n revolutions plus some time, we need to take into account the period of the orbit and add that to this computation. So we are aiming at further taking into account searches of uncertainty in the impact model. In fact, writing the variation of the velocity of the asteroid along the tangent normal out of plane reference frame, we not only take into account scalar uncertainty associated to the beta factor, but we also take into account misalignments between the 2 delta V's. Namely, we can represent the 2 delta V's as a cone, let's say, in which the delta V of the asteroid has a misalignment associated to the angle alpha between the 2 vectors. And then there's the angle gamma that's going from 0 to 2 pi, which is associated to the rotation around the delta V of the spacecraft. So there's a misalignment due to the unpredictable behavior of the impact. So to go from the deflection to the impact plane, we make use of these relations, which come from the Gaussian equations from variational theory. In it, we assume again that the perturbation, let's say, is an impact. So we have an instantaneous variation of the Kepler elements. And in all of them, you can see it's purely geometric relation with the with the addition of the final term of the variation of the mean anomaly. In fact, this is not associated to the variation of the geometry of the orbit, but rather to the variation of the period of the orbit, which was underlined in the previous presentation. This is a key factor in the deflection scenario, because even if the impact is not changing the geometry of the asteroid's orbit that much, the fact that we are changing its period allows the asteroid to speed up or slow down with respect to the Earth passing by, and then to miss it. So it's a key term in this representation. This is associated to the variation of the energy of the asteroid, associated again to the variation of the semi-major axis. And we assume that the impact is performed at a true anomaly of 0. Once we have computed the variation of the Kepler elements, we can compute the variation of the position in radiant and transversal out-of-plane reference frame associated to the deflected asteroid. This is commonly done because, again, since we're dealing with perturbation theory, because the variation of the Kepler elements is much smaller than their actual value, we can assume that the B-plane is associated to the unperturbed and undeflected asteroid. And so the reference frame which we're using to represent the deflection is again associated to the unperturbed asteroid's orbit. So here are the values. There's just some geometry going on, and we can compute the variation of the position of the asteroid. From there, we can go to the B-plane, which has been defined, I guess, at least 3 times during this week. And it's the plane on which we are representing the impact, on which we're quantifying the probability of impact in this generalized case. So to do this, we first compute the relative velocity between the asteroid and the Earth. And then we build an orthonormal reference frame from which we can construct what's called the B parameter, which is basically the radius on the B-plane, the length of the vector on the B-plane between the impact position and the Earth position. So, and that's it for the, let's say, asteroid deflection part. Now we get into the uncertainty quantification. As said, we are doing this to take into account uncertainties associated to parameters characterizing the deflection scenario. So in general, to do this, we can introduce what's called polynomial chaos expansion, which is a technique allowing basically to go from a finite dimensional continuous map to an infinitely dimensional but discrete map. In fact, what we're doing here is taking a functional x of z, in which z are random variables associated to some mathematical objects. And instead of dealing with the functional itself, we spectrally decompose it on its probability space. So we approximate it as a sum of terms in which we decouple the dependence from the probabilistic quantities to the non-probabilistic one. In general, the C term in the sum can be a function of time if we're dealing with a propagation, can be a constant, as it is the case in this problem. But nevertheless, it is not a function of the probabilistic quantities associated to the uncertainty. What's a function of the probabilistic quantities is the phi term, which is a polynomial. And so the idea of the polynomial chaos expansion is to construct a basis of polynomials of a given degree, defined a priori, which are orthogonal with respect to each other. Orthogonal with respect to the inner product defined by the expectation operator associated to the probability distribution of the z parameters. We do this to be able to spectrally, that's why we call it spectrally decompose, because we want orthogonal basis that can best represent the initial distribution, the initial finite dimensional continuous map. So the equation 20 describes this orthogonality condition, the inner product between phi and phi k is just the integral over the probability space of the product between the two polynomials, with the scaling factor of the probability density function of the z parameter integrated in the probability space. Because of the orthogonality condition, these polynomials are such that the expectation matrix is diagonal, so that if j is not equal to k, the expectation of such inner product is 0. And this is an interesting property of these polynomials that can be used to efficiently propagate the uncertainty. To build these polynomials, there are many techniques. The most efficient one is the three terms recursion relation, which can be used to create univariate orthogonal polynomials. And you can see the formula is given here, and the an and bn coefficients are again some expectations, probabilistic quantities associated to the expectation operator. Here we are building univariate orthogonal polynomials, but we can easily make use of tensor products to go from this representation to one in which let's say the probabilistic quantities are more than one. This is the case, for example, in the deflection scenario depicted before, in which we have beta, alpha, and gamma. So the coefficients instead associated to the expansion, the C coefficient given in equation 19, can be estimated with two different approaches. The first one is regression. So the idea is simply sampling the omega space, then evaluating the functional over these samples, and then fit this set of samples to the polynomial chaos expansion, for example, in a least square sense, or in any other sense that can be seen as suitable for the problem. Another technique is the pseudo-spectral projection, which makes use of the orthogonality condition between the polynomials. But we will focus on the regression. In fact, equation 23 is based on the spectral projection, and this involves a high-dimensional integral. So in order to avoid this, we make use of the regression so that we can build, even if the mapping is nonlinear, we can always build a linear mapping approximating the nonlinear functional of the probabilistic space, and then the computation of the expectation operator necessary to evaluate the coefficients of the expansion can be done straightforwardly using analytical formulas. In fact, the expectation of a polynomial is straightforward. So for this work, we're using the regression technique, in which every time we have a functional that we want to represent with this polynomial chaos expansion, we simply produce a number of samples and then fit those output samples with the polynomial chaos expansion. In practice, in this scenario, the quantity we're interested in expanding is the b parameter, which is a function of z, which is a vector taking into account all the uncertainties associated to the deflection. And then from there, we can compute the probability of impact, which is defined as the integral between 0 and r of the b parameter. Here are the results of doing this. This first result is associated to a beta modeled as a Gaussian distributions with mean 2 and standard deviation 0.5. And here, the misalignment is not taken into account yet. We have alpha and gamma equals to 0. And we add to the delta t associated to the variation of the true anomaly one entire evolution from the impact, from the deflection to the impact. And you can see that a reasonable value of the uncertainty associated to beta. In fact, in the literature, one can find values ranging from 1 to even 5. There is a big spread of the b parameter. On the left, you see the b parameter. On the right, it's just the representation of the b plane with the probability distribution of zeta and chi, the two the coordinate system associated to B-plane. And you see that there's a probability around 0.5 for the asteroid to impact the Earth, which is non-negligible. We do the same, asking ourselves, if we trust the uncertainty quantification associated to beta, what's the delta V we need to impose to the asteroid to have a confidence of, let's say, 0.9 for the asteroid not to hit the Earth. And we can do this, and it turns out that we need to go to a delta V of 37.5. And this allows us to stay below the 10% risk of impact. It's also straightforward to change the probability density function associated to the uncertain parameter. And for example, here we take into account a uniform distribution between 1 and 3 of the beta factor. And again, we are around 0.5 for the probability of impact. The other parameters are kept the same. Again, we can ask ourselves, what's the probability what's the delta V necessary to have a probability of impact below 10%? And it turns out we need to improve, to increase even more the delta V, going to 42.5 kilometers per second to have a probability of 0.098 of impact. And you see we're shifting the probability distribution outside the white circle, which is the projection of the Earth on the B-plane. So these results instead is associated to a more uncertain case in which we are assuming the 3 sources of uncertainty. We have the enhancement factor going from 1 to 3 in a uniform distribution, the alpha angle defining the misalignment between the delta V of the spacecraft and the delta V felt by the asteroid going from 0 to 10 degrees, so a small misalignment, and then the gamma angle going between 0 and 2 pi. And you can see that here the probability of impact is 0.75, which is a different value from the one in which alpha and gamma were kept to 0. So we have an increasing probability of impact due to this misalignment that may play an important role in the construction of a mission that's robust in the sense of being able to deal with such an uncertainty. Here, I'd like to underline how there's a computational time associated to this polynomial chaos expansion, which is much lower than a more classical Monte Carlo analysis. You can see that the time associated to this computation is 2 to 7 seconds, while the Monte Carlo is 1950. So it's almost an order of magnitude of difference in the computation, the computational cost. So here we present another result, which is building on previous works defining what's called the smart cloud approach. Here we are before the impact between the spacecraft and the asteroid, and we're aiming at using a cloud of small spacecraft, which are put on a transfer orbit to impact the asteroid. With a spread. That is, we are performing a Hohmann transfer in this case, using a distribution of delta V's and of angles alpha defined as before, so that we have a spread of the cloud, and we can be more sure that we're hitting the target. And from there, we can again compute the delta V felt by the asteroid, and from there compute the probability of impact between the asteroid and the Earth. So this is a simplified geometry.
Sorry for the interruption. You have 3 minutes left.
Okay. So thank you. So we perform a Hohmann transfer with an uncertain delta V, both in amplitude, but also in direction, which it's not an Hohmann transfer anymore, but you get the idea. And from there, we can compute the probability of impact between the cloud of spacecraft and the asteroid. And here, using a delta V with a standard deviation of 3.6 meters per second, you can see that the probability of impact between the cloud and the asteroid is 0.5. The asteroid here is really small. It's 97 meters of radius, a value taken from the, assuming the asteroid's density is equal to the Apophis one. Again, we're using the alpha uncertainty, and we can ask ourselves the same question as before, I mean, a similar one, in which we say, what's the reduction of the spread of the delta V necessary for the cloud to impact the asteroid with a 90% probability? And it turns out to be 1.45 meters per second. Again, from there we can compute the delta V felt by the asteroid, integrating the expectation of the indicator function, which is the probability for the B parameter to be inside the asteroid, and the delta V associated to such realization of the stochastic mapping. And we get a delta V of minus 0.01 in the tangential direction of the motion of the asteroid, and then a small one associated to the perpendicular one. So in general, we're aiming for future works to refine the dynamical model so to take into account perturbations and even stochastic parameters and processes inside the dynamics. Then we're aiming at combining uncertainty quantification with the gravitational keyholes presented in previous talks and include mission design constraints. Here are some references for this work. And thanks a lot for listening. I'll look forward for your questions.